Hey students, it's Mr. Lucido. Just wanted to create a quick video for you all um, in response to a question that I'm getting about your analysis questions from today's group lab. And specifically, a lot of people are asking about question number 3. So question number 3 right here says, using your data from part 2, calculate the water potential of our potato cubes. Our room temperature on the day we did this lab was, we're going to assume 22 degrees Celsius. Show your work and explain your reasoning. So to do this, we have to think about how do we calculate water potential? Well, so we know water potential is adding pressure potential and solute potential. For this experiment, this was done in just an open container. So we're going to assume that our pressure potential was zero bars. Which means we still need to solve, though, for solute potential. And by this point, we know that it's equal to negative ICRT, right? So if we can find our solute potential for the potato cubes, then we can determine our water potential. Okay, so from that equation, what do we know based on the context of this experiment? So first, let's talk about I. So for the I value, this is regarding our solute, which in this case is sucrose. We're working with sucrose solution, so that's the solute that's relevant to this experiment. And we know sucrose has an I value of 1. We're going to come back to the concentration in just a moment. We always know what the R value is, which is 0.831. And now we know what the temperature is, which is equal to 22 degrees Celsius, but we have to adjust it to Kelvin, so we add 273 to get 295 Kelvin. All right, so then that leaves C. What does C represent? Well, it represents the concentration of solute inside of the potato cubes. Do we know that? Well, not yet. That's what we actually have to solve for using our data. So how do we do that? So before we get into looking at our data from part 2, just a quick reminder of the context. So in part 1, the intention was that using the dialysis bag technique, where we put the different colored sucrose solutions inside of the dialysis bag and measured over a set period of time how much percent weight gain was measured for each dialysis bag. And we have individual measurements and class average measurements. And what we can see is that using this data, which we plotted on a graph, this is a graph I took from group 1. I just want to provide a citation there. So we can look at this data and we can predict which colored solution corresponds to which concentration, right? Because that was the premise of part 1. And the idea is here that the higher the solution concentration in the dialysis bag, the more water is going to diffuse into that dialysis bag because it's got a lower water potential. So water is going to want to rapidly move inside that dialysis bag. So in this case, the yellow solution, when it was placed in the dialysis bag, it caused the dialysis bag to gain 14% weight increase. And since that was the highest, we can match that with the highest possible solution molarity from the context, which was 1 molar. And then I just went through and looked at decreasing percent weight changes and matched it with the next lowest level of solution molarities. So from this, we can determine what our solution molarities are. And when we go to part 2, which were the potato cubes, this time we have potato cubes that are placed in these different colored solutions that now we know which solution matches which concentration. So I've added them in the table, just like it prompts you to right here. Now, with that in mind, this experiment, this part 2, involved waiting a set period of time and then measuring the percent weight change of the potato cubes. But notice some potato cubes, they lost mass, and some potato cubes, they gained mass. So if we want to determine, well, what's the concentration of solute inside the potato cubes, that is of sucrose, well, what we can do is we can actually plot the concentrations with respect to the percent weight changes. And what we're going to get is actually, if you do a linear graph, you're going to get a line that actually intersects at the x-axis. And again, this is a graph that group 1 made. And what you can see is on the x-axis here, we have the increasing concentrations, right? On the y-axis, these are our percent weight changes of the potato cubes. And right here, we have an x-intercept. And so as we see the percent weight changes, they're decreasing the higher we get in the solution concentration. And I want us to think about, one, what does it mean when the potatoes gain mass versus when they lose mass? What does that say about the relative amount of solute inside the potato cube versus in the solution? And then also, what does it mean when there's a percent weight change of 0? Right? Because that's what this x-intercept is representing. It would be the scenario where you place potato cubes in a solution with a concentration of, it looks like, just above 0.4, so maybe like 0.45 or maybe 0.42, right? If you put potato cubes in that concentration of sucrose, this graph predicts that there would be 0 weight change. In other words, it would be isotonic. So we can determine the concentration of sucrose by finding the point at which it would be isotonic. Okay? So with that in mind, we now have the concentration of sucrose that is inside of the potato cubes, which will allow us to solve the equation negative ICRT that we need in question 3. So I hope that was helpful. Please reach out if you have any questions, and hope you have a good weekend.